Hi, my name is David Cohen-Tanugi. I'm 28 years old, and I just finished my PhD at MIT, where I worked on developing a more efficient membrane to turn salt water into fresh water. I came to the idea of addressing the challenge of the water crisis through an interesting route. I was a physicist for my undergraduate studies and was very interested in China. And learning about China and its current environmental problems, I realized how important energy, climate change, and water were going to be in the future. I then worked for an environmental organization focused on clean energy policy, and coming to MIT to try to make a contribution on the technology side, I realized there was much more need for new water inventions in the field of physics and material science and applied physics, where a lot of effort is already going into new batteries, new solar cells, and while those things are needed, I saw a huge gap in water technology, and that's how I decided to try to solve a bit of the water desalination problem.
The world faces a grave water problem. From California to China, we're more and more aware of the lack of fresh water for drinking, for agriculture, for industry. And it's too bad because, after all, there's a lot of water on Earth, but 97% of it is in salt water form. If there were only a process that we could use to take salt water from the ocean and turn it into fresh water. Now, there is a mature water desalination industry out there. It exists in the Middle East, it exists all over the world, but the technology has not changed fundamentally in the last few decades. Water that comes from desalination is still expensive, still energy intensive, and it's not a viable solution for the full water crisis today. I think I've helped find a material that could change that. It's called graphene. It's shown here in the middle, and it's a 1-atom thick layer of carbon. As a PhD student in the Grossman group at the Massachusetts Institute of Technology, I helped show for the first time that graphene could be used as a filter, as a membrane in other words, to let water through and separate out salt ions for fresher, more efficient water desalination. Furthermore, in addition to showing that it was possible, what we discovered is that because graphene is 1,000 times thinner than the membranes that are used using polymers today, water can flow much faster than through conventional membranes. What that means is that you can get as much as 2.7 times more fresh water per unit of time if you're desalinating, for example, brackish water. And similarly, graphene is very strong. It's got the tensile strength of diamond. And if you optimize the process correctly, you could actually save 46% of the energy in the desalination process using a graphene membrane. So really, the innovation is huge. If we're able to develop it to its fullest, we'll have contributed to the water solutions in the 21st century. But there are also a lot of challenges ahead. In particular, a lot of my work was simulation and theory-based. So I showed it was possible, and I showed what it would have to look like. The next big challenge, of course, is to actually produce a prototype that has pores like this one that are big enough for water molecules to go through and small enough to reject salt ions. That's something that my research group at MIT and numerous other research groups in universities and large companies around the world are now working on full-time with this objective of taking nanotechnology and passion and addressing the problems of water in the 21st century. Thank you.